Today's lesson will be about state changes, otherwise known as latent heat. Um, to find these notes, just go to March 25th. There's a version of these notes there. Plus, you should read the water ice little 2-page note package there to read. And if you are interested, you can read the textbook pages found between pages 288 and 295 of that resource package. If you want, there's some questions. I see I clipped that wrong. There's some questions on page, it looks like 295, if you need some extra materials to try. So the main takeaway today will be about state changes, and that's going from a solid state to a liquid state to a gas state. These are otherwise known as phase changes if you do other research on your own. If you add energy to a substance, if you add enough energy to a substance, you can make something go from a solid state and melt and turn into a liquid. Likewise, you can make it go from liquid into a gas if you reach its boiling point. If you remove energy from a substance, you can cause it to go from a gas, condense to a liquid, and then solidify into a solid. So every element, every compound on Earth has this ability, but for the most part, you will only typically see water in any of these three states all across the globe. Outside right now, you will typically find it in all three states. Well, you can't see the gas, but it is out there in all three states today even. So before we get into that, we should really talk about water, because water tends to be pretty special when it comes to latent heat. If you get into thermodynamics or go take your power engineering course, you spend a long time learning about the properties of water, especially for when you have to work with boilers. So there's a lot of physics that goes on with the thermodynamics of water. So we end up spending a lot of time talking about water. And since we're going to talk about water, we should probably point out something that's very different about water. And I'm certain you guys have seen this difference at least once in your life. Case in point, if you freeze it, water is the only substance that will, one of the only substances that will actually expand as it goes from a liquid state to a solid state. All other substances will contract if you're freezing them. They will shrink. So if you put a can of pop in the freezer because it's warm and you want it to be cold, and then you accidentally forget about it, or you forget to set a timer, you come back to this mess with the Diet Pepsi, or if you're lucky, you end up with this mess with the Coke and you catch it just in time before it's about to burst. That's because the can itself is shrinking because it's losing heat energy, and when you lose heat energy, you tend to shrink, contract, if you will. But the water inside the beverages, that's the main ingredient to every beverage, is water. It is going to expand, and so the container gets smaller while the liquid inside gets bigger, and you have a bit of a burst. So if you're unlucky. So water tends to be something known as an anomalous substance. So what that means is, for the most part, this is how we assume the volume of a substance is going to react as you add heat energy to it. So the temperature is going to go up, the volume is going to go up, and it's more of a linear fashion. This is the predicted thermal expansion of all substances, right? And for the most part, water does do this, but only between the temperature ranges of 10 degrees Celsius to 100 degrees Celsius. It will expand normally. However, water tends to be anomalous, which is a fancy word for different or special or strange, because it is actually most dense at +4 degrees Celsius. So between 0 and roughly 10 degrees Celsius, water does this dip where, as you start from 0 degrees Celsius and you keep adding heat energy to it, it tends to become slightly more denser around 4 degrees Celsius, and then, less dense, slightly less dense around 4 degrees Celsius, and then it starts to go up in volume as the temperature tends to increase. And typically around 10 degrees Celsius, it starts to behave more like our ideal theoretical predicted expansion of all of the substances. So water tends to be special for that reason. So that's one of the main reasons why ice floats. It becomes less dense as it becomes solid. And so that typically means the water that's underneath in its liquid form is actually going to increase in temperature as you go further down, which makes it possible for aquatic life to still be alive in the dead of winter. So it's actually a little bit warmer. I wouldn't recommend putting your hands in the water. It'd still feel cold regardless, but it is a little bit warmer as you go down. And if you get really, really, really deep down, then pressures start to change, and this scale tends to be a little bit different, but we're talking about normal standard pressures at this point. We won't get into strange higher pressures, lower pressures, and all the stuff that goes along with that. So what's actually happening is, if you remember the particle theory of matter, the kinetic molecular theory of matter, when a substance is in its gas form, the gas particles tend to be spread out quite a bit. They're moving with lots and lots of energy because they have a high amount of heat. So having around lots of collisions, if you start to remove that energy from it, it will start to condense. The particles get closer together. You now have liquid. If you remove more energy, you'll get a colder liquid. And when it's a colder liquid, there's actually, when it comes to water, there's actually less space between the particles when it's a cold liquid. So once you get to that freezing point with water, they start to crystallize and form an actual structure where there ends up being lots of gaps between all the molecules. And so because of that, its volume expands a little bit and its density decreases. All other substances do not do this. They tend to be more dense when they are in its solid state. So water tends to be very special for that reason. And so you should read up a little bit more about that with that little handout that's found online. We're going to get to the actual math of this. So the math of your specific latent heat is a really simple equation. It's just taking the to figure out the quantity of heat energy to cause a substance to go from a solid state to a liquid state, or from a liquid state to a gas state, or vice versa, going back down. You just need to know how much mass you have in the material, and you need to know what your specific material is. And so that's where the L comes in, your latent heat value. I've seen this L be an H in other media and textbooks. Most stuff I saw was always an L, but you might find it to be an H if you do your own digging. So I'm going to use an L for our purposes. So the specific latent heat definition says the quantity of heat energy required to change the state of a unit mass of substance. So delta Q is still going to be the quantity of heat transferred. We measure that in joules, but you're often going to be in the hundreds of thousands to millions of joules. So don't be surprised if a lot of the answer keys on the practice problems are written down as kilojoules or megajoules, because they're quite large. Mass, of course, we're doing the physics portion of thermodynamics. So again, we're going to stick with kilograms. If I give you something in grams, please convert to kilograms, because if you look at the latent heat units, the latent heat value is joules per kilogram. So you'll have to always make sure your mass is in kilograms. Your chart will be written down as kilojoules per kilograms because all the latent heat values are quite large. Unlike specific heat capacity, where the numbers were always in the 100s for the most part, these latent heat values are in the hundreds of thousands for most substances, maybe tens of thousands for some substances. So expect to see the units to be written down as kilojoules per kilogram. Notice this is not temperature dependent. Unlike specific heat capacity, that was very much temperature dependent, because specific heat capacity was defined by the amount of heat energy needed to change the temperature of a substance. When you're dealing with a state change, the temperature does not change at all. So there's two variations of latent heat. So it depends on what you're doing. If you're going from solid to liquid, or vice versa, liquid to solid, you want to use the latent heat diffusion value. So latent heat diffusion is the quantity of heat energy released when 1 kilogram of substance solidifies without changing its temperature. So it was defined for the purpose of water in mind, because water at normal room temperature is liquid. If you're going to get it into its solid form, you'd have to remove heat, and so therefore everything sort of fuses together, and that's why this is defined. It's the same coefficient that you'd use if you are melting. It still seems kind of weird to call it heat of fusion when you're trying to melt it, but you'll just have to get past that. Then the other definition, the other term you're going to use is known as the latent heat of vaporization, and that's just the quantity of heat energy needed to vaporize. So turn a liquid into a gas. And so for that, we use the symbol L with a little tiny v. And of course, the temperature, again, does not change in the middle of a state change. There's no extra definition for latent heat of condensation. You would just use the same latent heat of vaporization, because again, it's assuming we're going from water in its liquid state into a gas, because again, it's more common for water to be in its liquid state at normal room temperatures. So often when you're doing a calculation involving latent heat, it's handy to keep this chart in mind, because very often you're not going to be doing just latent heat during a state change. So this chart has water from temperatures -40 to +130 degrees Celsius. And when you add heat to it, starting down below where it's ice, just like we had in January, we had a few days that was pretty close to -40. Definitely in its solid state. So there's a little picture up there. Water is in its solid state, so it's ice at this point. If you add heat energy to it, it's not going to melt, but what's going to happen is you'd have to use your specific heat capacity just to change the temperature of the ice, just to get it to its melting point. So ice, water has a melting point at 0 degrees, and water, steam has a boiling point at 100. I expect you guys to just know those two values. Things like silver or lead or nitrogen, I don't expect you guys to know what its melting point and boiling point are, but water I think is common enough that you should just know those two numbers. So when you get to a melting point at 0 degrees for water, when you're at the melting point for water, the temperature will not change until it is all one substance. And so what's happening at that point is you're going to have a little bit of both. You're going to have water in its solid form mixed in with water in its liquid form. So you'll have basically a slush. That's what your Slurpees are basically. You have your ice and your water all in the same state, or not the same state, all at the same temperature, because it's not all one type of phase yet. So therefore the temperature will not change until all the material is melted away. Once it's all melted away, you can now, if you keep adding heat energy to it, it will now start to increase in temperature. But while it's under a state change, no temperature change will occur. So whenever there is a temperature change, again, you'll want to use your specific heat capacity until you get to a boiling point. And when you're at a boiling point, it flatlines again. So you're still adding energy to it, to the substance, but there will not be any temperature change, because it takes a lot of energy just to change state. So when you add energy to a substance, if the temperature doesn't change, that means your substance is in the middle of a state change. When you're going between the liquid gas, gas liquid phase, you would just still use a latent heat, but you'd have a different value for your latent heat constant. After that, once it's all one state again in its gas state, it would just be a matter of using your specific heat capacity equation specific for steam. So that's something you'll just have to know when you're adding heat. Likewise, if you're removing heat, you would just, instead of going up a staircase, if you want to think of it as a staircase, you would just go down a staircase, right? So when you're removing heat, basically, you would just have the opposite effect. When it comes to temperature, that one should be pretty self-explanatory. When you do a change in temperature and you're losing heat energy, you're going to end up with a negative value for your energy in the end. But when it comes to your latent heat values are all defined as positive values. So it'd just be up to you to know to make them negative when you are actually doing the math behind this. So if you download your work problems from that web page, you'll have a small chart. It's not as big as the chart for specific heat capacity, because for the most part, you'll be dealing with water. There's a few other things in there just so you can just see them for yourself. But for the most part, you'll be working with water, especially if you're planning on going into power engineering in your future, because that's the main thing that powers a lot of steam engines, and that's steam. So things like ethyl alcohol, lead, and mercury, I don't expect you guys to know what the melting points are. So silver has quite a high melting point, so it's frozen until you get to almost 1,000 degrees Celsius, and it stays liquid until you get to almost 2,000 degrees Celsius. Whereas water is 0 when it melts. That's how the Celsius scale is defined, and boils at 100. And again, that's how the Celsius scale is defined. So what I'd like you to do, if you printed this off, great. If not, then not a big deal. But I usually recommend that you make some edits to this chart just to kind of keep it straight for yourself. When you are melting a substance, you're going from solid to liquid. That's when you want to use your latent heat of fusion. So for water, it's 335,000 joules of energy for every kilogram of mass. So if you have 1 kilogram of ice, if you want to turn it at 0 degrees Celsius, you want to turn it into water at 0 degrees Celsius, you'd have to add in 335,000, again, that's what the kilo stands for, joules of energy. So when you're going from solid to liquid, you use these as positive values. If you're going the opposite way and you're trying to freeze something, you have to remove heat energy from the substance. It's up to you just to put those negatives in there. And so that's why I just type it down there below, put a little negative symbol. Just try to remember that as you do your word problems. On the flip side, when you try to vaporize a substance, so again, you'll often be working with water, but you never know what I'm going to throw at you. So with water, it's going to boil at 100, and in order to cause the liquid water to turn into a gas, you actually have to add in 2,260,000 joules of energy for every kilogram of water that you have. So typically, it's written down in the form of kilojoules per kilogram, so 2,260 kilojoules, or 2.26 times 10 to the 6 joules for every kilogram. So it requires a lot of energy just to cause water to go from the liquid state into the gas state. And that's mainly because, according to the kinetic molecular theory, a gas has the highest energy of all 3 states. If we're not, of course, talking about plasma. That's a topic for a much different day. Likewise, with liquid to solid, so when you're trying to freeze something, if you're trying to condense a gas, you would just have to remember to put a negative in front of these symbols, or in front of these numbers. So let's just try a couple problems. I'll do this one here just to walk you through it. So how much heat energy is required to change 2 kilograms of ice at 0 degrees Celsius to water at 0 degrees Celsius? So the temperature is there to kind of indicate that we are at its melting point, but the temperature doesn't change at all. One of the biggest issues with latent heat questions is students tend to forget that there isn't a temperature change during a state change. So typically you write down what's given to you. Latent heat questions, if they're written like this, are not too hard. Just a matter of identifying that you got 2 kilograms of mass, so you state your mass. You have ice and water, so that's basically H2O. So you're going from a solid state to a liquid state. I would just expect you to know that ice is solid, and when I say water, I am referring to the liquid state. If I'm going to talk about water in the solid state, I'll usually call it ice. So therefore, you have to look at the chart. So latent heat of fusion is what we're going to use, and that's 335 kilojoules per kilogram, because again, we are going from its solid state to its liquid state. So from there, just do the quick little math equation. Q is equal to mLF. So your latent heat of fusion, the energy required is just a quick little multiplication. 2 kilograms times 335,000 joules for every kilogram. So you cancel off the kilograms, do a quick little bit of math. You should end up with 670 kilojoules. Or if you'd rather write it down out of a metric prefix form, you can call it 670,000 joules if that is what makes it easier for you, or call it 6.7 times 10 to the 5. Only 2 sig figs for this question, because 2.0 is kilograms is 2 sig figs. My answer keys will probably reflect the first answer. So do make sure you know how to interpret the answer keys at least. But if this was a test or an assignment, I would accept any of those answers. So if you were similar question, still going to use water, we're going to take 500 grams of water at 100 degrees Celsius and convert it to steam at 100 degrees Celsius. So again, there's no temperature change. This is strictly a phase change. Again, if I give you mass in grams, please convert it to kilograms, and then recognize that you're going from a liquid to a gas. And so you would just look at your latent heat of vaporization. And for that, for our water, it's 2,260 kilojoules per kilogram, or 2,260,000 joules per kilogram. And you're using the exact same equation. The only difference is you want to use your latent heat of vaporization. So there's a little tiny V there. After that, it's just a matter of plugging in numbers, just like the last question. So I will point out that the last question, we went from solid to liquid. This time we're going from liquid to gas, and I have 1/4 the amount from example question A. I have 1/4 of that mass amount. And if I actually want to convert it into steam, I require quite a bit more, quite a bit more energy just to do that. So it gives you a rough idea. Now, in order to convert 1/2 kilogram of water into gas or steam, it's going to require 1,130,000 joules, or 1,130 kilojoules. Right, and you can write it down in different forms, of course. I didn't write it down written long form because I don't feel like writing down a whole bunch of zeros. If you'd rather call it 1.13 megajoules, so big capital M for million, if you want to call it that, that's good too. And of course, scientific notation also works. 3 sig figs are used because 500 has a little tiny underline for that 0 to the far right, so therefore we have 3 sig figs. So we'll do one more question, and this question is going to be a bit of a longer question. So this is where we're going to involve changing temperatures as well as a state change. So unfortunately, this question might take 10 minutes to go through. If you want to pause the video now to go take a break and do something else for a few minutes, that's fine. But we'll go through this right now. Otherwise, so for this question, how much heat does a refrigerator freezer have to remove from 1.5 kilograms of water at 20 degrees Celsius? Oh, there's a typo there, should be the word at, to make ice at -10 degrees Celsius. So you're going from room temperature water and you want it turned into ice at -10 for whatever reason. I like to kind of draw a picture. So I just copied and pasted the graph from quite a few pages ago at this point of what's actually happening here. So we are removing heat energy. So that means since we have a temperature change in this question, it's very handy to kind of visualize what's happening in the staircase, right? Since we're removing heat, we're going down the staircase. And so that also means I like to kind of point out the temperatures are involved. So 20 degrees Celsius would typically be between 0 and 100, 0 and 100. So 20 would be somewhere around here, which puts me in the liquid state. Okay, -10 degrees Celsius would be, of course, below 0, which puts us in the solid state, so ice. So that means if you look at this quick little chart, that tells me I'm going to have to change my temperature. So therefore, I need my specific heat capacity equation. I have to have a state change. So therefore, I'm going to have my latent heat equation. And then I have to change my temperature a second time. So therefore, I'm going to have to use my specific heat capacity equation again. So typically, if I'm just doing this on the board or in my own little notes, if it helps, I just kind of draw a quick little graph. I'm not too perfect about making my graph. I don't often label things properly, but this would just be for my notes off to the side while I'm trying to do a problem, just to visualize what's happening. I only draw in the parts that I need to know, and it would look like that for the most part. So if I get rid of the actual graph, the manufacturer graph, I might jot in pencil in my own little chicken scratch just off to the side there that when I have a slope of any kind, whether it's going down or up, I need to use my specific capacity equation. When I flatline and go horizontal, that's a state change. I have to use my latent heat equation. And again, I have to use a different specific heat capacity equation. So I typed this one out for the most part because I felt that my chicken scratch was probably getting unbearable to look at. So this question will require quite a few steps. So you can see there is 3 equations to use. So it's going to look ugly before it looks pretty. So first off, we need to figure out the terms. There's a lot of terms to recognize. In order to find how much heat energy needs to be removed, you have to identify every single term involved. So therefore, the mass, 1.5 kilograms. We're assuming we're going to keep that mass the whole time. We also have to identify what materials we're using. Well, we're using water according to your chart on your specific heat capacity, because again, in its liquid state, we have to use specific heat capacity. So the specific heat capacity of water is 4.2 times 10 to the 3 joules per kilogram degrees Celsius, or just If I convert it, so 10 to the 3 just means kilo, so I just convert it to kilo because I know offhand that this is probably going to be a large number by the time I'm done. So I just did a quick little conversion there. That's what my water is going to be. I'm also going to point out the temperatures involved. So water is going to go from 20 degrees Celsius initially, and it's going to go therefore to 0 degrees Celsius when it's in liquid state. You can't just go from 20 to -10 and call that a change in temperature of 30. Right? We can only change our temperature for one specific state. So this is our liquid state. Liquid state is going to go from 20 to 0, and you'll just have to stop at 0. 0 is not written down in the question. When it comes to water, I just expect you to know that, right? Or look at your chart at the very least. So know when you're going to have a state change. So you're only going to have a temperature change between whatever the current temperature is and your boiling point or your melting point, your condensing point, or your freezing point, whatever point that you're going to. We're going to the freezing point. So therefore, I'll just find my change in temperature of water. Change in temperature is always final minus initial. So I didn't show all my work. 0 minus 20 gives you -20. Water's handy for that because 0 is a lovely number to put in any equation. It just makes the math a lot easier to work with. So I'll just get rid of that other line and just use the change in temperature that I need. And that is just defining this section right here. So you have enough information, you can calculate the change in energy of this if you want, and just write it off to the side. Next, pardon me, I'm going to skip my latent heat, and just since I had the specific capacity chart in front of me, I decided just to steal the specific capacity of ice while I was at it. So I'm just skipping the latent heat section for the moment. So I'll steal the specific capacity for ice, because therefore I have ice down here below when as I go from 0 to -10, so I have another temperature change. So therefore I need my specific capacity, and I just quickly didn't edit 2.1 kilojoules per kilogram degrees Celsius rather than scientific notation. And the initial temperature of ice is going to be 0 degrees Celsius, and the final temperature of ice when I'm all said and done is going to be -10. So likewise, I need a change in temperature, final minus initial. So final temperature minus initial temperature. -10 is my final, -0 is my initial. So that number actually doesn't change because again, 0 degrees Celsius is a lovely number to stick into any math equation. So that makes it pretty nice for my parameters. I don't have to restate my mass because my mass won't change for every single one. As you see, mass is in every equation, so it's just still 1.5 kilograms. Moving on, if I steal my latent heat of fusion, so remember I'm going from a liquid state to a solid state, that means I need to take this number, the 335 kilojoules per kilogram, and I need to make it negative. So that's something you'll have to remember. So I have a negative number there for my latent heat of fusion, and that's all I need for this part right here. It's a latent heat of fusion. It's missing the F from there, but this is just the basic equation. Typically, I'll put a subscript next to it. And these are all the parameters I need in order to actually proceed with my total energy. So I'm going to shrink this screen up a little bit. You can kind of make out the numbers there just off to the side, but I need the space to do the rest of the math. So I need to find the total energy removed from the water just to make ice. So my total energy is the sum of all of my quantities of heat energy. So sigma is just add them all together. Delta means, well, the energy is changing. So, and Q, of course, is my quantity of heat energy. So I have 3 steps of my ladder. You can kind of still see this, or staircase, not a ladder. I have 3 steps. So I have that incline. So that is when I'm in my liquid state. So call it water. Sometimes I just call it liquid. I have my freezing point. So my latent heat of fusion. So that's where this comes in, QF fusion. And then I have my change in quantity of heat energy of when it's in its solid state, which I just have ice. I think my online notes uses liquid and solid for these 2 guys, but this one's a little bit different. So if I color code them just for no other reason than I like color coding, my liquid state, I'll use blue. My change in state, I have no idea what this color is called. We'll call it, I don't know, figure it out, teal maybe. And then my change in my quantity of heat energy for my ice is going to be purple, because why not? Mass is in every single one of them. I didn't need a subscript for all my masses, but I gave them one anyways, but I can just factor that out because it's 1.5 kilograms for every single one of them. So this is just how I like to do some of my math. To me, it makes it look a little bit easier if it's all in nice factored form. So after that, it's just a matter of plugging in all your terms. So your specific heat capacity of water in its liquid state is this. You have your change in temperature of my water to be a negative value. So you'd multiply those two guys together. You have your latent heat of fusion value for solidifying your liquid water into ice. So please remember that should be negative 335 kilojoules per kilogram when you're removing heat energy. And then of course your specific heat capacity of your ice and your change in temperature of ice. So a big mistake here that happens is when people forget to make this guy negative, try to remember that all three of these terms that are colored are either going to be, so I'll use these ones up here, this total, that, and that should all be either all positive numbers or they should all be negative numbers. There's no in between. There's no positive, negative, positive, or negative, positive, negative. It's just all negative, 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 or positive, positive, positive. So try to make sense of that when you're doing your problems, because that's usually the first point where people do make mistakes. So just try to be aware of that. So do the math, cancel off your temperatures for your two specific heat capacity equations. The temperatures cancel out and you're left with kilojoules per kilogram, which is handy. So when they're all the same unit, you can just work it through. So again, I have three numbers now. They're all negative. I can now just combine them all together, get negative 440 kilojoules per kilogram, and then it's just a simple matter of canceling out your kilograms and then just do the rest of the math. So in order to convert 1.5 kilograms of water at 20 degrees Celsius to make ice at negative 10 degrees Celsius, you have to remove 660 kilojoules of energy. So that's therefore the negative. So that was a little bit of extra work. If I went from the gas state into the solid state, I'd have two more steps I'd have to incorporate. Or if I was going from solid to liquid to gas, it would still be 5 steps. 5 equations is what I should have said. But it shouldn't be too much more difficult than what you see in front of you. Just be a couple of extra steps. The methodology will still be the same. And again, it's negative because we're removing heat energy. So I'll stop there because I could probably go on from there 10 minutes if I wanted to. I think this lesson was pretty long as is. So there's 7 questions assigned for a latent heat. A couple of them are pretty quick and simple, like the first 2 questions that we did together. And a couple of them will take quite a bit of extra paper to work it all the way through. So do try to do these problems. And if you have questions, just send me an email or take a picture of your issues that you're having and then send it to me as well. We'll try to work something out together. All right, sorry for making this one long. I'll try to get them shorter. Take care.